Okay, good afternoon. Thank you for being in time. So, it is my great pleasure to introduce Professor Jean Sulem for the next plenary presentation, invited presentation. Jean Sulem is currently professor at École des Ponts, Paris Tech, prestigious school of engineering, very known in France and worldwide. He has led one of the major research centers under two different configurations. First, as CERMES from 2010 to 2020, and then as Laboratoire Navier until 2024. His work has significantly shaped the field of rock mechanics, which contributions ranged from bifurcation theory to constitutive modeling to thermo-hydromechanical processes for geomaterials. Professor Sulem is also editor-in-chief of Rock Mechanics and Rock Engineering, and he was the recipient of several prestigious awards, including the Vardoulakis Lecture Award and the Science Achievement Award from the International Society of Rock Mechanics. Professor Jean Sulem will talk about the new challenges in rock mechanics and how to integrate them into engineering education. Dear Professor Jean Sulem, the floor is yours for about 30 minutes.
Thank you. Thank you very much. Thank you, Adele, for the kind introduction. I would like to thank the organizing committee for inviting me to give this talk. I'm very happy to be here, and I enjoyed very much all the talks that we had up to now. So, indeed, my topic this afternoon will be related to rock mechanics, and I would like to share with you some thoughts and about the necessary new skills that we have to provide in engineering education to address some new challenges. First, I will start with a very short and general overview about rock mechanics and rock engineering applications. And one characteristic is that there is a wide range of professional activities related to rock mechanics, from civil engineering, underground construction, rock slope, rock foundation, but also a large field where rock mechanics is involved is the domain of energy-related geomechanics, especially oil and gas engineering, so production, mining, geothermal systems, and in the last decades we have seen the importance of underground storage and sequestration for CO2, for hydrogen, or for waste, in particular nuclear waste, which is a very important topic, especially in France, and in general reservoir geomechanics. Topics of rock mechanics is taught in engineering geology to understand the mechanisms of folding, faulting, fracturing, site investigation, hydrogeological investigations to assess the rock and the rock mass properties, study the mass movement, subsidence, and the methods, the tools to prevent, protect, stabilize. Domain of seismology, for fault, earthquake mechanics, rock dynamics, wave propagations, geophysics, geophysical investigations, in situ determination of in situ stresses, and in general rock physics. So very wide range of topics which require a wide range of skills which are provided in the training of engineers and researchers in different format, in different content, depending, of course, on the curriculum, on the frameworks, from undergraduate, graduate, or doctoral studies. Also, the importance of continuing education, workshops, short courses, and, of course, the importance of practice in the training. And as in other domain of engineering and geotechnical engineering in particular, it's important to develop technical, scientific expertise, scientific reporting, ability to address complexity, to account for uncertainties, to address problems which are at the frontier between several disciplines, decision-making, and interaction also with stakeholders. So some of the skills are provided in scientific disciplines, and a wide range of scientific disciplines, as we have rock mechanics, engineering, geology, geophysics, seismology, but also fundamental topics like mathematics, numerical methods, and I will insist later on that, probability, statistics, computing, and data science, and of course, laboratory and field testing. But other disciplines also, which we know are very important for the engineer, like management, legal and administrative aspects of project management, the know-how on crisis management, and the communication to the general public, to the media. This is also important skills that the engineer today must have. Starting with the basic training of rock mechanics, as it is taught in most institutions, at the undergraduate level, we generally find these topics, starting from strength and deformability of rocks and discontinuities, linear elasticity, then strength criteria, rock joints, discontinuities, some basics of rock testing. Also, as you know, in rock engineering, the empirical methods, which are based on rock classifications, are very much used on different systems. And in particular, they are used in consulting offices, in projects, to assess the rock mass mechanical properties, but also to have first design of structures, for example, in tunneling. Rock slopes, mostly we teach about the various failure modes and the limit equilibrium models, rock foundation, and in underground construction, mainly ground characterization, excavation methods, and rock support design. So we see that in this basic rock mechanics teaching, we speak very little, as opposed to soil mechanics, of fluids, of water. And we know that rocks are porous, and they will likely contain one or several fluid phases, whether it's water, air, gas, and oil. And I believe that it's very important at early stages of rock mechanics teaching to introduce poromechanics. And in particular, I insist on these aspects of taking it into account poromechanics and other couplings in view of the new challenges that we encounter in rock engineering. I would like just to emphasize two of them. The first one is related to energy transition and the development of geothermal systems, for which we have to assess the performance, the economic viability, the safety, in particular versus the induced seismicity, underground storage and energy storage, for which we have to assess the efficiency, the performance, and the long-term tightness. In these problems, we encounter often complex geological conditions, great depth, high temperature, and the question of risk control and acceptability by the people is, of course, central. And the other topic is the impact of climate change, rock slope embankments, and the effect of drying, resaturation, freeze and thaw cycles on rock weathering, coastal protections, and others. So, therefore, it's important to develop ability, skills, in order to explore, understand, model the involved physical-mechanical processes for large-scale and long-term predictions. And these physico-mechanical processes, they are multi-physics phenomena because they may include mechanical processes like damage, fracturing, cracks growth, and healing, multi-phase fluid flow, the effect of temperature, but also the effect of chemical or microbial reactions, as it is the case for CO2 or hydrogen storage. And these various phenomena interact in these multi-physics couplings. Also, they might involve different time scale, and it's important to assess the characteristic time scale of the various mechanical or physico-chemical processes, and also to determine what is the relevant time scale of the problem at hand for the engineer. We know that, for example, laboratory experiments, the relevant time scale is hours or days, but in civil engineering structures, it's 10 of years. For nuclear waste storage, it's thousands of tens of thousands of years. Earthquakes is seconds, seismic cycle is hundreds of years. So how to master these various time scales. Also, the processes that we are studying are at multi-scale. First, because rocks are heterogeneous at various scales, from grains, pores, microcracks to fractures or larger structures like joints and faults. The processes of damage and rock deformation occur at the grain scale, breakage, abrasion, crushing, frictional sliding or reorientation of grains, growth of microcracks and dilatancy. Chemical interaction between the pore fluid and the minerals, like in dissolution, precipitation, or swelling, occur at sub-micron scale, but it will affect the flow of the fluid on a much larger scale. It will affect the porous network of the fracture. And so at the engineering scale, which is the macro scale, we have to do this upscaling to define the appropriate equivalent homogenized continuum, for which we write some constitutive equations and also behavior of macro discontinuities, and also understand how the processes are interacted at various scales. So, for teaching geomechanics today, and mostly in the framework of advanced courses in graduate studies, I would like to focus on three topics, examples: couplings, failure, and cracking. And first, for coupled processes in rocks, poromechanics are taught in a rock mechanics course, usually contain the problem of fluid flow, transport law for a single or multi-phase flow in porous media. That session this afternoon is about unsaturated salts, and unsaturated rock mechanics is not so much taught, but we know, especially in reservoirs, that we might have several fluids in contact. So multi-phase flow in porous media is a very important topic in many applications: fundamental balance equations, thermoporoelasticity and plasticity. So concepts of mechanics of unsaturated porous media, fluid flow in fractured rocks. This is very important in rock mechanics. The rocks are discontinuous media. And also we teach some fundamental analytical solutions. For example, the pressurization or the loading of a borehole or hydraulic fracturing problem. Another important topic is the strength of rocks under coupled processes, for which I believe we have to go beyond a classical limit analysis, which can be done in some advanced course. We know the efficiency of limit analysis, which is commonly used in geotechnical engineering to compute limit loads. We can, of course, include the effect of pore pressure and the dynamics. but in many problems for which we have to study the evolution of the strength, it's important to consider the complete inelastic response of the structure of the material, because it influences both the conditions of incipient failure and also its evolution beyond. And in particular, this is important for applications to borehole stability, compaction subsidence in reservoir, slope stability, seismic slip, and accounting for the various thermo, hydro, chemomechanical couplings. And for that, the notion of stability and strain localization, considering the mathematical concepts of uniqueness and bifurcation for studying failure of materials, is very useful, and many works have been developed in the last decade in this domain. And we know that strain localization is favored by the softening behavior of the material. This softening behavior is due to the degradation of the rock properties, microcracking, grain crushing, but also to some other coupled processes, for example, the effect of pore fluid, temperature, or chemical reactions. For example, on the role of fluids in strain localization processes, we know the strong interaction between the inelastic volume changes, dilatant or compactant, and the change in the pore fluid. And the effect of the pore fluid, which interact with the rock mass, can result either in hardening or softening, whether the volumetric response of the rock is dilatant or contractant. So, for example, if we study the stability of undrained layer under shear, if the material is dilatant, the instability will occur at a state corresponding to the instability of the underlying drain behavior. But if the material is contractant, it will occur before. So this coupling is important, but also other processes like the effect of temperature. For example, when the material is deformed quickly, or if the rock mass has a very low permeability, then we are in almost undrained conditions, and heating will lead to thermal pore fluid pressurization, because the thermal expansion of water is much higher than the thermal expansion of the solid grains. So thermal pore fluid pressurization is a mechanism of softening because of the reduction of the effective mean stress and consequently of the shear strength. But also chemical reactions like dissolution, precipitation, thermal decomposition of minerals at high temperature will affect the solid and the fluid phases and influence the conditions for instabilities and strain localization. So we know that strain localization is not an easy problem, especially if we want to deal this problem using numerical methods. We have to be careful, because in the post-localization regime, the mathematical governing equations become ill-posed and should be regularized in order to have some robust computations. Otherwise, we face mesh dependency, because we have the tendency of strain to localize within a single element. So this has been largely studied in the last 30 years, and I believe that it's important that the method of regularization are based on the physics, and especially on the smaller scale physics, so introduce a material length that will limit the localization zone thickness, like it's the case in some continuum models, COSRA, or higher grade or non-local continuum models. Considering the modeling of cracking, there have been lots of works in the last 2 decades in the development of numerical fracture models for rock breakage, crack propagations, and coalescence. So mainly we can distinguish between 2 types of approach. one is called the weak discontinuity approach versus a strong discontinuity. In the weak discontinuity approach, the cracks are seen as band of strain localization, as we discussed just before, and so we can use the continuous approach for localized failure. And in the strong discontinuity approach, then we consider really the material discontinuities, so discontinuities also of the displacement field, and for which the basic course is mainly based on linear elastic fracture mechanics, introduce a notion of stress intensity factor, and the rock properties such as the fracture toughness and the criterion of crack propagation. But in a more advanced course, especially considering the effect of fluids, the notion of subcritical crack growth is important also to model the evolution of time of the crack propagation. And we face situations where we are not only having brittle rocks, but also semi-brittle or ductile rocks for which we might have crack propagation, and we have to consider also plastic flow, so the existence of a plastic zone at the crack tips and the cohesive zone models are efficient for that. And of course, in relation with fracture of rocks, they've developed teaching about laboratory testing. In terms of numerical models, here also we see two big families of models. One is called the sharp crack model. So indeed, the displacement is field is discontinuous across the crack, and for which the numerical models are based on finite element. But there are some limitations because it's high computational cost. We generally we can deal with a relatively limited number of cracks, and because the crack is propagating, we need to frequent remeshings. Extended finite element methods brings some improvement because the shape functions consider discontinuous displacement field, which permit to have cracks which propagate along arbitrary paths, no need for remeshing, but still the method is limited to introducing a rather limited number of cracks. Also, what has been developed, especially in the last 20 years, is what is called the diffuse or smeared crack model. So you see, as opposed to the sharp crack, which is the discontinuity, now the displacement field is assumed to be continuous, but with a very high gradient. So it's a non-local model because we introduce some length here corresponding to the zones of this high gradient. And it has some very important features in terms of numerical efficiency, especially a model which is now more and more popular, phase field models, largely applied to in rock mechanics. And it permits to consider many different physical contexts: hydraulic fracturing, heterogeneous materials, ductile behavior, finite deformation, multiphysics couplings, many advances in the last 10 years in this domain. And it can master crack nucleation, growth, branching, coalescence, complex crack paths, networks of cracks. But still quite costly in terms of computations and limited to small system. And also one word about some methods which are becoming more and more popular, and many PhD theses, publications are related to these mesh-free methods. So here we discretize the domain not in elements, but in particles that will interact with each other. This is the case for smooth particle hydrodynamics with many applications and material pond methods, application to fragmentation, impact, collision, fractures, multi-phase flow, but still computationally expensive and adapted to relatively small size problems. And if we want to deal with multi-scale analysis, the development of what is called hybrid model that will couple at a small scale one method, whether a discrete element or finite element, and at a higher scale another method. But the limitation is mainly related to the computational limitations of the microscopic simulations, and we see some research, for example, developing some database and use AI then tools in order to avoid repeating lots of microscopic simulations. One word about project-based learning, some general consideration. It permits to address complex and challenging questions, to address real-world problems, to apply and acquire the knowledge that we give in the class. Also, it permits a link between academic research and engineering applications. Learn how to make choices in the methods, and also, and this was discussed also this morning, how to have a critical look at this method, collaborate, discuss, share. Also, it's the opportunity in this project-based learning to make the students sensitive to scientific integrity, to produce results, not to please the teacher or the client, as we heard this morning. Scientific reporting, develop in general new skills, learn about decision-making, acquire autonomy, responsibility. So this is, of course, very important. And also the opportunity, for example, I give here the example of using numerical codes, but it could be also for a more experimental project. So to get good habits and good practice. First, how to choose the appropriate method, how to choose the appropriate code, and also what are the key steps, definition of, we have seen this morning examples of the size of the model, but to define appropriate time and space scales, time and space discretization. Very important to always check convergence, check mesh independency, have a critical analysis of the results, the relevance, the physical meaning, the limitations, scientific integrity, and also, and it could be also generalized to experimental work, introduce students with some good practices for managing and valuing research data. We know that it's very important in open science policy of the universities, how to store, to share, and make our results accessible. One word about continuing education, which I believe is very important for engineers. So this corresponds to advanced courses on specific and new topics, and also it's a good opportunity to bridge the gap between academics and practitioners. And this is some example of topics, modeling of THM processes, numerical methods with some advanced methods. Machine learning, I did not have time to speak about this, but we see both in research and in practice, and in practice in geomechanics, machine learning is playing an important role. Also, advanced experimental rock mechanics, particular imaging, fluid flow, dynamics, physical models. So, to conclude, just to emphasize, I believe for the engineer of today and tomorrow in the future, it's very important to have a very strong background in mathematics, physics, and mechanics. And to start with this, and then we learn the applications. Have good theoretical basis about couplings, develop computing skills, bridge academic research and engineering practice, and as we see that the complexity of the problems we have to face needs multidisciplinary approach, learn how to bridge different disciplines. And for that, I believe that master's and doctoral studies are very important for well-trained engineer. I know that in France, unfortunately, in companies, the doctoral degree is not so valued, but it permits for the doctors to have a real deep knowledge, at least of one topic, and be ready to learn other ones. Thank you very much.
Thank you, Jean, for this interesting presentation. We have time for 1 or 2 questions.
Yeah, thanks. David Airy from Sydney. Yeah. So you've suggested we're going to add a number of things to the syllabus. I'm just wondering what you're going to take out to achieve that.
Sorry?
So you've suggested we need to add a number of topics.
Yes.
Yes. So my question is, what are you going to take out?
Yes, but where do you take time for that?
Yeah.
But you don't need to teach everything at the same time. You have various frameworks, undergraduate studies, graduate studies, doctoral studies, short courses, continuing education, what you learn also by yourself or with your supervisor or with your colleagues. Yes, we face this problem because we have a reduced number of hours of teaching because we have to know everything. And we see also in my school that the schedule of the student is increasing and increasing. And we want them to have projects, but sometimes we think that we find that they do not have enough time to work deeply on that. So, well, in France, you know, the system is a bit different, which helps us in a way, because you enter in engineering studies after some preparatory classes, 2 or 3 years, where you get a good training in mathematics, physics, and chemistry. And then, for example, in Ecole des Ponts, you enter, this is the 4th year of university studies, and first you have, again, numerical methods, mathematics, and continuum mechanics, fluid mechanics, and you start soil mechanics only after, and rock mechanics even after. So this helps us because they have this basic training on which we can base our further teaching, including finite element training. But I agree with you, it's very difficult that this is what we discuss daily with our colleagues. We have to take this away, but we want to.
Okay. 1 more question, perhaps? I have 1 question from my side. You were talking briefly, very briefly, about the use of machine learning. How do you foresee the way that we can use machine learning in education, engineering education? To what extent should we teach the basics of machine learning, and what for?
Yes. So I think now in most engineering program, I see this in my school and in other engineering school around, machine learning is taught quite early in relation with statistics and the Department of Mathematics and Computing. So we can base on this, for example, in projects of rock mechanics or geotechnical engineering, how they can use these first basic courses to address some problem. For example, taking a large database of geotechnical data or of rock mass classifications indexes, and what do you do with this for answering this question or another. So we had, it was more for the student in the framework of projects, or for a longer term study in a PhD. For example, how machine learning tools can help in tunnel design. What do you do? This is.
So, thank
you very much.
Jean Sulem.